In Chapter 5, we continue our discussion of probability. Our focus will be on discrete probability distributions. This video will cover Section 1, where we'll learn what discrete probability distributions are and apply them. We'll calculate and interpret the expected value and standard deviation of a discrete random variable. So what is a random variable? The book defines a random variable as a variable that takes on different numerical values based on chance. It's a variable, so it can vary from experiment to experiment. The variable itself represents the possible numerical values that we could get from a random event. So remember we talked about discrete before. Discrete is a countable number of items that a variable could take on. Continuous would be infinitely many possible values that a variable could take on. Now I went ahead and put this picture here so that you could see the distribution for discrete looks sort of like these bars here. And a distribution for a continuous random variable, which we'll talk about in Chapter 6, looks more like the normal bell curve. So this section of the textbook focuses on discrete random variables. Remember, discrete means countable. So a discrete random variable is a variable that can assume only a countable number of values. These can be many possible outcomes, such as the number of complaints per day, or the number of rings before a phone is answered, or it could be only two possible values, such as male or female, defective or not. These are graphs of two different discrete probability distributions. So the graph on the left has only three possible values. That random variable can only take on the values 10, 20, and 30. The height of the bar in this graph represents the probability of getting a 10. So we see 10 has a 60% chance of occurring. 20 has only a 30% chance of occurring. So we've listed out the possible values of x and the associated probabilities. That's what we call a probability distribution. So the graph on the left shows 21 possible outcomes. You see each of those possible outcomes listed here. And the height of the bar again represents the probability of that possible value coming up. Some more concrete examples of discrete random variables. We could talk about an experiment where we roll a die twice. And suppose we're interested in the number of times the number 4 could come up on the die. X could be 0 because we might not roll a 4 either time. We might roll a 4 one of the two times, so we would get a 1, or we might roll a 4 both times, so we would get a 2. The random variable x can take on the values 0, 1, or 2. A similar example, if we toss a coin 5 times, x could be the number of heads that come up. So if we toss the coin 5 times, we might get no heads, 1, 2, 3, 4, or 5. Those values are our possible values for the random variable x. So let's walk through a particular example. Suppose the experiment is tossing 2 coins, and we're interested in the number of heads we get. There are 4 possible outcomes that could happen. If you toss 2 coins, you might get 2 tails. You might get a tail on the first coin and a head on the second coin, a head on the first coin and a tail on the second coin, or 2 heads. So if we count this up, there are no heads here. That's our x value of 0. There's 1 head in this case and 1 head in this case. The random variable's value is 1, and there are 2 ways that that happens. Here we have 2 heads. That would be the random variable's value of 2, and there's only 1 way that that occurs. There are 4 possible outcomes, so there's a 1/4 chance of getting no heads, a 2/4 chance of getting 1 head, and a 1/4 chance of getting 2 heads. So this is actually a probability distribution here, but in a table form. We can easily convert that into a graph. So the graph below shows the individual possible values for x and the probability of each of those values occurring. When we generate a probability distribution, we want to list out all the possible values of x and their associated probabilities. It's important that the x values do not overlap. They need to be mutually exclusive. We also need to list out all possible values of x, so it needs to be collectively exhaustive. Each of the probabilities have to be between 0 and 1, and the sum of the probabilities needs to add up to 1. In Chapter 3, we started calculating means and standard deviations. The assumption was that each data value had an equal chance of occurring. So we could use Excel to calculate the mean and the standard deviation quite easily from a list of data. When we have discrete data, each x value may take on a different probability. So to calculate the mean of this probability distribution, we need to calculate what's called the expected value, which is just a fancy way of saying the weighted average. So this notation here means the expected value of x. And what we do to calculate this is take each x value, multiply it by its associated probabilities, and then add them all up. So suppose we're back with our example of tossing 2 coins, and the value of interest is the number of heads. We can compute the expected number of heads, or the expected value of x. The expected value of x would be no heads, that's our first x value, times the probability of no heads occurring, that's 1/4. 1 head times the probability of 1 head occurring, 2 heads times the probability of 2 heads occurring, and add those pieces together. We get an expected value of 1, which makes sense. If we have a fair coin, we would expect the head to come up on average once every other toss. Now that's on average in the long run. This expected value is really the long run average of the experiment. So we could easily toss a coin twice and get 2 heads. But in the long run, the average would be 1. We can calculate the standard deviation for a discrete random variable also. Remember, the standard deviation is a measure of spread. In this case, it's a measure of spread in the discrete distribution. So the notation should look familiar. We've got our sigma. Sub x is there for x being the random variable. And that's going to be the square root of the sum of the squared deviations times the probability of each of those deviations. X minus the expected value of x is that deviation. How far is the individual data value from the average? Square that, multiply times the probability of that deviation squared occurring. Add those all up and then take the square root of that. So we'll use our example of the 2 coin tosses again and the number of heads that come up. Remember, we just calculated a few moments ago the expected value was 1 head. So our standard deviation is the square root of each individual data point minus the expected value squared times the associated probability. So remember, we had the chance of 0 heads coming up. We subtract out the expected value of 1, square that, and multiply by the probability of getting no heads. There's a 25% chance that we could get no heads. 1 minus 1, so we had 1 head could come up, minus the expected value of 1, square that and multiply by the probability of getting only 1 head. 2 possible heads minus the expected value of 1, square that, multiply by the probability of getting 2 heads. If we do some simplification here, we see the spread in this distribution is 0.707. The expected value and the standard deviation of a discrete random variable must be calculated by hand. There's no function in Excel that will do this for us.